Hello there. So, remind people that expect people to come to class in general. Though I'm not annoying about it, but
take a video.
But so I'm not sure about homework 6. Homework 6, I'm debating between two things, and it can be either to review the choice or to ask you to do both, or that I'll succeed to convert to one of them. One is HDR. So again, it will be possibly both of them. Possibly I'll let you to choose. Possibly I'll decide. So one is the HDR that is we'll talk about today, a high dynamic range of images. Another option is to piggyback on the pool that you already have with a reflection of the pool. And there is too many details here, so I don't expect you to do the whole thing, but that would be the liquid model. So since it's related to this part, to the lava, because you think about bulbiness that we discussed last meeting, implicit representation, and bulbs that goes all the way to the surface of the water of the pool, and then got opened. It doesn't need to be Z details, just got to the open. You will see how the lava bulb get to the surface, create a little bulb, little mountain, kind of ball-like, but not exactly. There is some animation of the surface, but that we'll talk about when we'll get back to talk about animation. And that would be that together with the rest of the things of the pool, where every pixel you essentially just need to decide what is its elevation. So it's not too hard modification of the pool that you have for homework 5. So that's idea from today, and I'm still scratching my head. The other, the other ideas that would be maybe standalone, maybe with other, is let's talk a bit tone representation, and before that, any questions about what we discussed last time? Implicit representation, surfaces generating the mesh out of it. We talked about marching cubes. Hopefully, all okay. Tone representation, and mostly tone correction. So dynamic range of the eye versus dynamic range of the monitor. Now, very, very different, and eye is much more sensitive. And I will use a few terms that are not exactly the same, like if you're physics, or I can think about yours that will be short for the level of inaccuracy. But I will talk about brightness or luminosity or intensity, and I'll refer to it as the same thing. And it's not. But it's how strong a pixel is. How strong is the light for a pixel. And it's even and you can measure how many watts. Well, you know, different wavelengths have different energy, but then there is also how many photons are getting there, and you can measure it in various ways. And for us, if we'll just take for a pixel the value of R plus G plus B, it's somehow a good approximation. If you want a bit better approximation, there are some constant here that will give you what is the intensity of the pixel. But again, luminosity, intensity, brightness, not the same thing, but we'll refer to them as the same thing. And one of the reasons that they are to the messiness in all these terms is that there is the energies that we are measured as a physical property, and then there are our emotional sense reaction to how do we interpret this intensity. We'll talk about this one a bit more, about the subjective part of measuring the intensity. But again, the take home from this slide is that when we'll talk about the intensity, we'll think about the R plus G plus B. And we're taking a picture, and this picture is taken inside a relatively dark room, not strongly illuminated, a few internal lights that you see over here, and the ratio between the darkest pixel. You don't have anything that is completely black, maybe, or at least we measured anything that you get at least value of 1, assuming that 0. Some pixels are completely 0, so we ignore them. What is the intensity of 1 versus what is the strongest intensity? And so assume that I took this image using as sensitive camera as you can get. Really, really, really sensitive camera. What would be the intensity per the strongest versus darkest pixel? And they will be roughly 1 to 1, maybe 100 to 1, but still same, not huge gap between orders of magnitudes, not anything similar to what we see in the next pictures, which shows an office inside the building, but this office has a large window, so daylight, which is way, way stronger, comes from the window and illuminates it, and now the darker parts versus the most illuminated parts, now we are in the ratio of thousands. Again, that's the image that I'm taking, not in how I display it. This person sitting outside, exposed to the sunlight, but he is in the shadow, so somehow. In the shadow, now that we are in 1 to 25,000. Now, person darker shirt versus bright sky, 1/400,000. Sun versus dark sky, well, in this ratio. And cameras are cool with taking all these pictures. Okay, that is the sensors have enough many values, enough many resolution per each sensor that you can take these pictures with most cameras. But in our display, we'll assume that R is between 0 and 255, and the same for G, same for B. So I need to make something for the image before I show it to you. Otherwise, it will not look good. So that we'll play a lot with this image that has very bright areas and very dark areas. And after HDR, we can see the trees, the branches, even though they are in the much darker part, and we can see the details of the clouds on top, even though the original difference of intensities of this portion of the image are huge. And the big idea about the HDR is that we're going to massage the intensity values. We're going to massage the intensity values, but when I massage them, I have to be very careful that not to massage a value so this pixel is now equal to its nearby pixels. Well, at the moment that I made a pixel equal to its nearby pixels, they look the same. So I'm losing special details. Things starts to look blurry. So all the transformation that I'll have to make to the image, I'll have to respect the big idea that things should be relative and relative to intensities near you. If you're going to make changes, try to make them sensitive to the area. So what I suffer should be what pixels near me should suffer, or at least we are all going down, we are all going up, so relativity between us is somehow stable. Okay, here is the same image, but without HDR, completely brushed, very bright over here, very dark over here. Another image that we'll play with, very bright over here, no details on the sides over here. Okay, so our big problem of tone correction, tone representation, is that the dynamic range of the world is between the dimmest pixels that we can still notice with our eye or with our camera up to the brightest pixels. In the same image, could be roughly an order of 10 to the 6. And we are going to copy it into a dynamic range. We are going to map every intensity here to an intensity here. Intensity, again, the R plus G plus B to R plus beta plus G. To every value here to every value here. But this value is somewhere between 1 and 255. Only 2 orders of magnitudes versus 6 orders of magnitudes. Okay. So let's start with the very naive question. I'm going to give you an image in this homework that needs HDR, needs correction, which means that I took it from a source that has a pretty high intensity as a camera. Did we see a format of a file that can represent more than 255, 256 values per pixel, per channel of pixel? Quick question. Geeky question. Did we see any format that allows us to work with better resolution of intensities?
Is it the dot like O something? It starts with an O. Not that one.
Probably, except, but I don't know. At least I don't know for this one.
Okay.
I don't know if we talked
know about them here, but I know there are like floating point image formats. Like
We'll get to more specific formats. Among the formats that we saw so far, was there anything that allows? Basically, there was only one that we kind of discussed what happened in the file. At the very beginning of the bunny, remember? We had the header. The whole file was just a collection of the whole file, excluding the header, was just a collection of RGB, each one as a byte, RGB as a byte, the string of bytes. So it was completely raw data. But what was a header? In the header, we could have said that each value of RGB would be represented either as a 1 byte or 2 bytes. And that was in the header itself. And if you are represented as 2 bytes, then of course you have 2 to the 16 values of color resolution. Okay, so we'll introduce other formats that are more popular for high dynamic range images. People remember what I was talking about? Even though you got a reader, when Josh was teaching it, you had to write your own reader. I gave you, or Amir gave you the reader of the file that created as an image, as an array directly from the file. Okay, yeah, so we want to change without changing the color. I'll briefly mention HSV, very, very briefly. I'll talk about ways to correct the image, alpha correction, beta correction, gamma corrections. These are all local operations. They take one value of a pixel here and map it to one value of a pixel from here using alpha, beta, gamma. But looking at these pixels couldn't care less about what the neighboring pixels' values are. And then we'll talk about global operation and talk about high pass and low pass filters while doing so. So going to be quite interesting for those in the ppm, you can specify that it's 2 to the 16 bits. But there are other formats as well. So the RGBE is a popular format. I'm not expert enough to tell you if it's the most popular, but a popular format for high dynamic range images. And what does it compensate for? So let's think about floating point number, standard floating point, LOI 3. I can write this number as a floating point, or the binary equivalent of this number, and then I can write this as a R, this as a B, which would be and G, which would be 1.99, to have each pixel to represent as a floating point. I can do it. That's pretty long, say 4 bytes per each. So for the 3 I need 12 bytes. The observation here is that pixels tends to be, or it's okay to assume that for a pixel, the exponent of these 3 terms is the same. The pixel is either illuminated or not illuminated. Not always true, obviously, but true enough to be practical. So let's make this assumption, and let's use only one exponent. And now the pixel, represented as 32 bits, would consist of 8 bits for the red, 8 bits for the green, 8 bits for the blue, except that each such number you need to take times 2 to the power of 103. That is, the exponent is common to all of them. Except that it's not 103 because with 8 bits, if I want to, I can represent a number between 0 and 255, or like so, I want to represent both positive and negative numbers. So instead of 0 to 255, I'll represent only numbers between minus 126 to plus 126. That is, this number that I'll write here at the end, I'll take the exponent, 103, and subtract from it 128. Okay, so whatever the numbers that you see here, subtract from it 128. So the RGB of this combination is R is 145 times 2 to the exponent is 103, 103 minus 128. So you have exactly enough numbers, since what you have in the exponent can go up to 255. You're reducing 128. What's the range that you're getting? Anything between 127 to minus 127 based on the exponent. Okay, and that's common commercially. So 32 bits per channel. And alpha not mentioned. So in this homework, these files, I don't know if the format is happy with alpha. At least in this version, it is not. RGBE, if I remember right, does not allow alpha. Okay, now when I'll ask you to correct the intensity of something, I can go the whole way and think about it as the color in HSV coordinate system. HSV, I want to change only the intensity and not the color. Doable, I'll mention a bit more how it works. Here it's actually even a simpler hack in this homework. What do? I'll take the intensity of the input I, R plus G plus B. Maybe I'll divide it by 3, doesn't matter. Maybe you have constants here, roughly linear combination of these 3 values. That would be the intensity. Now, what I'm going to do to this pixel in the correction is I don't want to change its color, but I do want to change its intensity. So I'll have to compute a new intensity. New intensity, target intensity will be I prime. If it's very bright pixels, I want to make it dimmer. If it's very dim pixels, I want to make it more bright. I prime. And now the new RGB is just whatever was the old RGB. That's 3 numbers, times the ratio between target, or between what? The old intensity and the target intensity. Okay, so if the old and the new are the same, then the RGB just stays the same RGB. I and I prime. So in this algorithm, you are taking RGB values, compute their intensity, decide what's a new intensity, and change linearly, that is, multiply the RGB values by a constant, the ratio of the new versus the old, and of course, when you multiply by a constant, you are careful that if this number is larger than 255, then you chop it to be 255. That's as much as you can I'll assume that you all have monitors that can represent between 0 and 255. Okay, that's, I assume that many of you have monitors that are more sensitive than this, but we are not, I assume that none of you is a gamer. You all have old style monitors. Okay, so linear scaling, that is, I'm just playing with the brightness. And I can speak in photography about exposure, organized slides, and I can speak in photography about overexposure, that is, in the camera is more the light than the sensor can really measure. Or, in other words, if you have two sensors that both got different values of light, but are so strong that now they both report. This is as high as we can report. That would be overexposure. Okay, and for the display, 2 pixels P1 and P2, that shows the maximum intensity that the pixels can show, even though they actually in the original image have different values. That would be the overexposure. Underexposure is that the sensors just start to work when you give it intensity higher than something. Otherwise, it shows us completely black. You wish it was black. Well, whatever it is for 0, 0, 0. Anything that is truncated to be 0, we'll just think that it's underexposure. It makes less sense when I talk about a specific sensor. It makes more sense when we are getting back to this image, and it's quite clear that all the details here are invisible to us because this is overexposed, and all the details here are not visible to us for the opposite reason of underexposed. Okay. But good news, we can correct them. We can reveal the details so our monitors are happy to show them. Simplest formula. The intensity out individually per pixel. The same constant per pixel. CO out equals alpha. Alpha is one parameter that I want to change, called the gain. The in, I'm looking at the in intensity times alpha. Alpha is one potentiometer, one slider that you can change, plus beta. Beta is a bias, the other sliders that you can change. Okay, that's the simplest. Just do linear transformations of intensities. By itself, not that useful, but a bit useful. Why do I need 2 parameters? Because my input intensities are all the way from here to here, and I want to now, what's the problem with this image? Here's the image, it has only one line of pixels. Here's the image, it has all these lines of pixels. And here, and as I'm moving in the image, the pixels become more and more brighter and brighter, from 0 to 55. What's the problem? Why do I feel the need to correct it?
Because we're not using our full color space.
Yes.
Yes.
I don't know. Essentially, we have 255 pixels. Each one has a different intensity, but because of just pigeonhole principle, you are pushing 255 values into only 50 values, meaning that many of that 5 values over here are mapped to the same value in the intensity. So you're getting a much blurrier images. You are taking 5 pixels, say I assign to you 0, value 1. Another 5, I assign to you value 2, value 3, value 4. And The original 5 that I assigned value 1, originally they did have different values. So what do I want to get from it? I'll just change alpha, the slope, so it will get all the way, at least high, at least all the way to this place. Maybe it would look less realistic, but at least the spatial resolution, it's a term that I use a lot, the spatial resolution, the fact that every pixel had the different values, there are details hidden in this image, you will see all the details on this way. Without the correction, it will look just much too blurry. The same thing, even more painful. Here, not only that I'm mapping all the pixels to the value between 50 and 100, again compressing them, but on top of it, I don't use all this interval over here, all the weak values. So that's why I want both the bias and the gain. So I want to move this curve down and now change the slope. So I used everything in the image. Make sense? And similarly in the other two examples. That again you can change by just changing alpha and beta. Now, as we'll see, alpha and beta can work directly on the intensities itself, or can work on the log of the intensity. We'll speak about the log scale and why we prefer the log scale inside. Okay. So you have values of two different, of 2 pixels before and after the corrections. The ratio of delta, what was the difference of the intensities before versus what was the intensity after, assuming that S1 is very bright and S2 is very dark. Ratio of these intensities is exactly where alpha change. You're changing the contrast between very dim but not 0, light of 1 versus light of 255. Alpha allows you to increase the contrast. We need desperately more examples coming up. Okay, and well, and similarly for beta, we saw what the beta, the gain change, where we again beta was helping us because there is a big part of the dynamic range that we are not using. It would be nicer that this will be mapped already to 0. Okay, so we have the alpha correction. Alpha is a gain. Beta correction. Beta is a bias. And we have the gamma correction, which is gamma is a gamma correction. What is a gamma correction? The new intensity is, well, you're still welcome to use the alpha plus beta correction as well. So it's a alpha times the old intensity plus beta. And then put it all in the power of gamma. Gamma is the third potentiometer slider that you can use. Okay, so you decide about the value gamma, depending on your vision, depending on what you like to see, or that your display will decide about it by itself, but you'll decide about gamma between 0 and 1. We need to see the influence of gamma on graph itself to understand why different value of gamma can rescue different values of intensities. Now, even for the alpha and beta, sometimes instead of working directly on the intensity, I will prefer to take the log of the intensity. Say log 2, that's not really crucial. Make it log 2, the base of the log, doesn't matter. And now I want to do alpha correction, that is change the gain, but if I multiply the log by gamma, it's just like putting the gamma over here, and then do the reverse operation. So Gamma correction is like doing alpha correction, just half in the log scale. Okay, let's try to define what we are trying to preserve with all these terms. Before we see more examples, we like the term of the special frequency. How many pixels do we need to move starting from pixel 1, 2, 3, 4, 5? Moving from left to right, 1 pixel, 2 pixels, 3 pixels, and the special frequency is how many values do I see? How many changes of up, down in the intensity do I see as I move from left to right? But high intensity would mean black, white, black, white, black, white pixels. Low intensity, many pixels that are dark, many pixels that are white, and so on. So what the parameters that we want to preserve is exactly the spatial frequency. If you reduce the spatial frequency, it means we are losing details. The things that are too close to each other now will appear exactly the same, which will give us the feeling of having the image blurry. But they all have the same intensity if they have the same color. Then they are undistinguishable. Now, there is much more in this graph than what I'm going to tell you about, but referring to the vision system, in this little diagram, here is very slow when I'm moving to the X. I start from very low spatial frequency. Things changing very slow here, and now my frequency is higher. I'm alternating between black to white pixels as I'm moving from left to right. Alternating from black to white. Here is big chunks that is white, whitish, a chunk that is black, white, black, white, black, and so on. But the frequency decreases. That is, this is unit half, this is unit 1, length 1, half, quarter, 1/8, 1/16, and so on. So, of course, I'm increasing the spatial frequencies, and to keep the image sharp, I'd like to be able to distinguish between them even though they are very close to each other, very high spatial frequencies, and it's great if I can still see that they are separate between them, which I could for a very strong image, or to be precise, if the contrast between the highest intensities to the lowest intensities is very strong. Once again, it was a convoluted sentence. If the contrast, this alpha that I had, is very large, very bright pixels, very dark pixels next to them, then my spatial frequencies is great. I can still distinguish, especially when I'm standing so close, I can still distinguish between the black, white, all the way up to the highest frequency, which is just a pixel. That if the contrast is high. Now let's start decreasing the contrast, that is giving less intensity to the bright pixels, more intensity to the darker one, and you notice that things start to look completely grayish, and it's much harder to notice the different lines. That is, we need the contrast in order to, the conclusion from here is that we need strong contrast, not only to have the image look realistic, but we need a large contrast to be able to distinguish special details. Think about it as the leaf of the trees. Strong contrast would mean that I can still see the individual leaf of the trees. Low contrast would mean that the whole part of the tree will appear as one blob. Okay. As I said, there is much more that goes into how our vision system actually interprets it. And Not to mention that it's depend on which part of the eye you're watching this part, because you know hunters versus gathering, where the danger is coming from, being able to notice movement at the night, and so on and so forth. So depending which part of the night, depending on which part of the frequency. Okay. Few examples of playing with alpha and beta and how it's overexposed, underexposed. No gamma correction here, just alpha and beta on the intensity itself. I would think that this is too much exposure. Look at the head, where pieces of the head start to be completely white as opposed to the original, and you don't see the details of the head, you lose details of the hand, and so on. So I would think that that's overexposed. The gain, the alpha, is, to my taste, too high. Over here, gain is too low. Over here, we are also losing details, but why are we losing detail in this case? Because the contrast is too small between two different points. Looks the same, so it looks much more blurry. Okay, and goes even worse in these two images. Again, you might feel individually different for different images here. And but I think that we all agree that comparing to this original image, there is tons and tons of details that we are missing in the other ones because of over or underexposed. So that's with alpha over beta. Let's throw another term of why do we like the logarithmic part out of it. Is that our human perception works in logarithmic scale. I think that it's true actually for all our senses. That is, that if I give you the feeling of something that is warm look, that is a bit warm or a bit illuminated, and I want to make it twice as illuminated, what you'll understand as twice as illuminated, I don't need to give it twice the amount of energy, how many watts are coming from you with this part. If I want to have it twice as strong, that you'll understand it as twice as strong, I need to actually multiply the energy by 2. And then I want to move it again by the same amount, I need to multiply it again by 2. Again, that is here I'm moving it. That's not a slide that I wanted to get. Maybe I don't have the slide. That you see it as a I'll show you an image that is commonly, you have seen it many times before, where this block is completely white, completely black, and what I expect you to understand as the middle point between white and black, so that's gray, but I expect this gray to be just in the middle of the way between black and white. The amount of energy, the RGB values that I need to give to it is, if that's 255 per pixel and that's 0 per pixel, this value that you'll claim that is half the way is probably not 255 half. The value that you want to give to this guy is probably not 255 half, unless it's already half corrected. Definitely it's not half the amount of energy between white and black, will not give you the feeling that it's half white, half black, that it's gray in half the level. You need some other value that meets you halfway. That's why you have such scale, and one of the reasons and because it's so individual, A and B, so much depending on which display you have, that's why when you are tuning your monitor, you'll have such an image and ask you to place gamma until it looks white. But looks white doesn't mean that physically you're giving it half the RGB value or half the energy. Okay, so, and the logarithmic part about our vision system is that we have huge dynamic range. We can see a very dark, almost very dark details. And then to make something that is just slightly brighter for us, we need much more energy. Something slightly brighter for us, much, much more energy. It needs to go exponentially higher. Okay, so with gamma correction, with white gamma, I can take, here is the original strip that where the RGB value changed linearly, but it doesn't look like it changed. The middle way. And here, after correction with gamma, arguably better. And here is more example of gamma correction. So what are we getting from gamma correction? So gamma, the intensity is between 0 and 1. After placing it in the power of gamma, it stays between 0 and 1. But every value of gamma gives me another curve. That is how all of them are monotonic. That is, all of them match a point on X to a single point of Y for every value of gamma. But which one works best for your image, for your taste, it's very individual. Okay, why is this good? Because they are non-linear, it's not a linear transformation, and it more works with more coherent with how our vision system, that is, that if I'm changing gamma because of my vision, is my senses works in logarithmic scale, it's just like I did alpha correction in the logarithmic scale. Practically, original image after values of gamma with correct gamma correction, I can avoid over and underexposed in the results, which I don't get in the other images. Okay, so far it was just a discussion about why you need the 3 parameters. Very wavy discussion. Yeah, again, alpha, beta, and gamma as a non-linear bias get them in many pictures. Yeah, we saw these slides before about the dynamic range. Yeah, how that, and that, as you know, everything is relative to how the neighborhood of the pixels behave. We understand the intensity as the intensity with respect to the nearby pixel, the environment. So alpha, beta, gamma were all done once I decided about alpha, beta, gamma. I decided about the whole algorithm, the whole formula that I apply to each and every pixel. I don't ask the pixel what happens near you. I really like this image. That's a great image about what are we getting by doing only local operation, only per pixel operation. So I assume that the camera was set. So there is no autocorrelation of the camera. So the camera is seemingly working just fine, which would mean that the intensity RGB of the headlights in the 2 images are the same. The lights arguably are on in this image, and they're taken with exactly the same intensity as you see it here. So why does it look so much more dominant here versus here? Because the remaining pixels are dark. We can understand the brightness with respect to the neighborhood. Same explanation, walk in the street, try to peek into your neighbor's house, and do it during the night when everything is dark, a part of the neighbor's apartment, versus a day where you see some reflection, but you still see into the apartment with the same intensity. Suddenly you cannot see into the windows because the reflection from the window is so much stronger than what comes through the window from the other apartment. Even though what happened in this apartment, what you see through the window, have the very same intensities, but comparing to other signals, it's now much weaker than the reflection, making it literally invisible. Make sense? So try to say value of a pixel by itself is meaningless, value of a pixel with respect to its neighborhood, important. Okay, so we have the tone mapping and eventually got to the display, and will not discuss much, not at all, not my expertise, the whole human sensing subjective of how we understand the image. But the big idea is that if I have the original image here after HDR, because I want to display it, but let's say that that's the original image with very high dynamic range, I cannot show it pixel by pixel, and you'll see the same dynamic range on the display. So I'm going to cheat. I'm going to heavily cheat, and in the sense that the image that I'll show you is not the original image, but it will look like the original image. I'll tweak your vision system so the original, the image that I'll show you will get the same quote-unquote feeling as if you have seen the real image in 3D, even though it's not. How do I do it? By playing with bright versus dim with respect to the neighborhood also, always. So, yeah. Let's move. Okay, let's take this original image. As I said, that's where we want to correct it. The tone mapping with that's image. I already squeezed from this image everything I could by using alpha, beta, gamma correction, and it looks terrible. Lots and lots of details are missing. Why? So that's why I need no non-local operations. Same goes here, the image after HDR. The image before HDR is either completely black because of overexposed or underexposed because of the darker part, but definitely you don't see the colors of the bark of the trees. With HDR, voila, looks great. But that's not overexposed spire, having much higher intensity over here. That's not underexposed, and you see the details of the tree, and you even don't see the hollow part that will appear very soon near the trees, and will be the justification of the triliteral functions. Okay, so what the big idea is that I'm going to take the image and I want to separate it into two images. Separate into more. I'll keep the color separately. There is an RGB value that I don't change the RGB value yet. I keep the same RGB value. But I will take the intensity at each point, and the intensities are what I'm going to change. So here's my input image, it has very high intensity, let's call 20 very high intensity. It has very low intensities over here. On the other hand, here is my monitor. That's the lowest level that a pixel in my monitor can show. That's the highest pixel. I just created what is about 5 different values of intensities per pixels of the monitor. So I need to take all this dynamic range. Once again, how do I understand it? It's like one row of the image going on the X, and the Y value is the intensity. So for pixel 2, that's the intensity at pixel 2. So that would be the image. Let's see if it happened in the form. Because okay, input image, very high dynamic range, and on top of it, you see that the spatial frequency is quite high. Right? That's why I added to it all these little teeth over here. These are like the leaf of the trees that you see over here. Here the tree is highly illuminated, but it has leaves that are very close to each other, correspond to the teeth. Out here, now the tree, other part of the tree is quite dark, but also all of these teeth. And these teeth are that's a special frequency. Special frequency is very high. Lots of changes, but the big idea is to let's separate it into fast changes and slow changes. Let's explain what do I mean by fast changes and slow changes. So again, why do I feel the need to correct it? Because every intensity here, I need to map into intensity between that's the lowest one, that's the highest one on my monitor. It's 255, but that's in the GeoGebra, the only values. So let's try, I have alpha correction and beta correction. What happened when I change beta? What will happen to the graph of this image when I change beta? Just show you part of the whole graph, but so just part of the image from here to here. That's good enough. What will happen to this graph? Remember, that's this part, except that I discretize it because you eventually have only 255 values on your monitor, 6 in the GeoGebra. So that's a discretization over here. I'll remove temporarily the original image, so you see this part better. What will happen to it when I change alpha? Or when I change beta? Let's start with beta again.
Move it up and down.
Just move up and down. You're moving, adding a constant. Here that you're pushing it up, you're pushing it down. Here it's too too small because you see that these values are outside the range, getting a value that is higher. Now I'm there. It's like the dimmest values that I can present on the image that is getting any reaction from the monitor. It is more than 0. And when I change alpha, of course, increasing alpha will make it help.
More wiggly?
It will increasing alpha will make it.
Will it make the wiggles more intense?
Yes, it changes the amplitude. This part, which will make it yes. So it will.
Wiggles.
It will go. It will go up. So here part of this image is overexposed, right? That's the maximum intensity that I can show, and that's the maximum intensity. That's the maximum intensity that I can show with a monitor, and you see in the original file that I value below it. So all the details here will show all look as overexposed, just a constant bright. Your look, none of these details, these cliffs, will be visible.
In that, is
So-
it like rescaling to just get taller?
So yeah,
or is
so
the
that was the
distance
best alpha beta that I can get. So at least right now I alpha beta corrected it. So at least in terms of the dynamic range, it all fit. But will I get the same spatial resolution? It looks more blurry than the original image. Well, it took me a lot of time to generate the value clearly, so the answer will be yes, because there is these teeth that you see over here. Why were the teeth more noticeable? Again, the individual leaves of the tree, why were they more noticeable? Originally, well, every such teeth has different value of maximum and minimum, enough for our eye to notice that there is a difference. After the alpha beta correction, since I compressed this huge dynamic range by 0.3, so I took this dynamic range into this dynamic range, the gap between the teeth are way smaller, implying that after discretization by my monitor, they are quite likely to receive exactly the same value out of the 6, out of 25, that the monitor can show. So I'm corrected as far as max versus mean values, but the spatial resolution went down dramatically. It becomes way more blurry than what it was originally. The teeth disappeared. Everybody understands the problem? You can compress, you can make it large, make alpha large, and when alpha is large, the gaps of the teeth remains, but now your monitor cannot show the very high values. It will show it here for the smaller values, but not for the higher one. Making alpha small enough so the dynamic range fits, and now the local values vanish. So what are we going to do? We are going to separate the image into two separate images. And to separate the image, it's not like the BSP. I will not have the left side and the right side. That's not this type of separation. It's a huge source of confusion. I'm not cutting it geographically into one piece and another piece. Instead, I think about I of P, the intensity at P, and I'll write I of P equals I1 of P plus I2 of P. So the separation is separation of the intensity. Each value is now the sum of two values that I'm going to compute. And it's going to be quite cool how I'm going to compute these two values. So again, its separation of every numerical value will be the sum of two values. So the image is now the sum of two images, but it's like pixel by pixel sums. I want to know what I have in the image at pixel 1, 1. What do I have at pixel 1, 1? What's the intensity at pixel 1, 1? I look at the two images that I create. At pixel 1, 1 here, pixel 1, 1 here, sum them up. That's what you'll have at this pixel. Okay, that's great. How am I going to do it and why? So what I'm going to do right now is take this signal, and think about it as a signal. It's all things that would be very trivial for people that took any ECE course, and I'm going to smooth it. The smoothing here could be convolution with a Gaussian or convolution with a tent or with a box. We'll talk about it much more. In this case, what I do as the s of x, the function s of x, is the original input f of x for every pixel. S of x is f of x. F is my input. S of x, what I'm going to return, which would be s for smooth, is f of x plus f of x minus 1, that is 1 pixel to the left, plus f of x plus 1, which is 1 pixel to the right, and all of it divided by third, multiplied by third. That is, I replaced every pixel, f of x, with the average of this pixel with the 2 nearby pixels. Maybe I'll do it with the average of the 5 pixels. Since it's not only a row, maybe it would be 3 by 3 pixels. We'll talk more about how can I smooth it. But what do I see as the result? I see as the result as s of x. Let's remove for a moment f of x. That's the original file. And s of x is what? Smooth function. It has the same maxima and minima, but that's a much smaller one. All these small teeth vanished. So what did I do? What is this S of x, S for smooth? It's a low pass filter. It allows you only to pass if you're changing really slow. What I'm doing is exactly what your car or bicycle are doing if they have suspensions. It takes a signal and it averages it with a road just next by or nearby and smooths the changes that happens out there. Also, if you have speakers, especially older speakers that has woofer and tweeter, what you send to the woofer, to the big speaker, is just the low frequencies. Okay, so that was S of x. That's the first function that I'm going to generate. The next function that I'm going to generate is more interesting. Next function is age of x. X here is the pixels that I'm working on. That's it, just x, 1, 2, 3, or ij, just which pixel I'm working on. Age of x for every x would be f of x minus s of x. Age of x is, remember the original function, minus the low pass function. And the age here stands for, say it, age stands for high. That's a high pass filter. What does it look like? Here it is. Slow minus high. It became the high function. That's what I sent to the tweeter. The tweeter cannot go that far in terms of amplitude or in terms of strength, but it can move very fast. This has all the changes that I had in the original function, going up and down very fast, but with very, very limited amplitude. Well, of course, it's a toy example that I tailored for it, but instead of moving from 0 to 20, it only moved from minus half to half, but extremely fast. Okay, so I have the low pass filter, the S of x, the smooth function, and from the smooth function, I got the high changes, the high frequencies. And why? Because the high frequencies, these are just the special frequencies. These are details that I really cannot compress. I want to compress to do alpha beta corrections, but I don't want whatever modification that I'm going to change should not affect age of x. Maybe I even want to overemphasize the age of x, because that's what shows me the special details, the tiny leaves of the tree with a black background. So I'm going to do alpha beta corrections, but not to f of x, not to the original part, only to s of x. So just sanity check. What can you tell me about age of x plus s of x? What is this function?
fx.
That's just the original function. I didn't change anything. That's just the original function f of x. What I'm going to do now is to take only the low part, and on this I'm going to do the alpha beta correction. I took the smooth part, and after the correction, I just showed for portion of the interval. After the correction, it's within the minimum and maximum. I do change and delete. And now for the slow part, I don't care about losing special information, special frequencies, because the special frequencies are all waiting for me over here. I can compress it without losing high frequencies, because it doesn't change that much. By definition, the low function changes very slowly as I'm moving from left to right or out top to bottom in the image. So what you see in red is alpha s of x plus beta. That is the alpha beta correction of s of x itself. And now what do I send to my monitor? At least, well, not yet, but at least what is the intensity that I'll send as a target part? The output from this part of the algorithm I look at alpha s of x plus beta, that's in dynamic range of the monitor, but it's lacking all the special details, plus age of x. Age of x is uncompressed. Remember, alpha here is 0.36. It really compressed the dynamic range. Age of x is not compressed. So it's age of x plus s of x. And voila, it's compressed to the right way, but the gaps, the jumps that you see, the jumps that they are all in the dynamic range of my monitor, and the jumps that you see between low and between every teeth up and down are larger than the gaps that I need from my intensity of the monitor. So they'll appear this and this, these two nearby points will appear as different intensity on my monitor. So I do see the different details, and it's all within the dynamic range. So that's the idea of exactly the HDR algorithm. Well, almost. So what am I doing? So all of it was in the intensity value. That was my original image, given as one of the files with very high intensity. That's when I try to show it without any correction. What do I do with it? I heap the RGB value of each such guy, but I also compute the intensity of each such guy. So that's a new intensity. And if you ignore the intensity and use, for example, HSV descriptions and just ask now, because of every pixel, just what its color, that's this image. It shows you the color, but the intensity is meaningless here, just as an exercise of what does this image looks like when it all has the same intensity and you just play with colors, but the RGB is the same. We don't use it. That's an intensity. Remember, intensity for every pixel, you're taking the R plus G plus V for every pixel. Got black and white image. That's what you're getting. You are smooth convolving it with a Gaussian or with a box. What I did here is just convolving it with a box called convolution, which for us just means replace every pixel with its own value plus a nearby pixels. Convolving it, just Gaussian just gives different weights. It's like a weighted average. So that's a smoothed image. That's a low frequency. That's S of X. And now, how did I get this one? I took the original image minus the low frequency. That's a high frequencies. See? You see that all the special details are stayed over here, but the gap, the contrast of this image is much slower. The difference between the highest to the lowest are very slow, are very small, just like in the example that we saw earlier in the high. Again, low scale, big region of black, big region of white. High frequencies, lots of very quick changes from white to black, but white to black respectively without any extreme high or extreme low. Okay, I took these two images. I take this nice image and reduce the contrast. So now that's a compression. Add to it the details. Add this image. This is this after alpha beta compression. Here are the details, the high frequency. Add it back to the image. And now, remember, we had this formula that said the new RGB is the old RGB times the ratio between the target intensity versus source intensity. I look for every pixel, say, what did I did to this pixel? Say I multiply it intensity by 2. Going back to the color, see what was the original RGB of this guy. Say, oh, I need to multiply by 2. I'll take the R multiplied by 2. I'll take the G multiplied by 2. What's the difference between this and the alpha beta correction? Here, for this point, I multiplied by 2. For this point, I multiplied only by half. It's not the same constant for different cases. It's the same constant per pixel, and this constant is what was the ratio between what you had versus what you're going to get after all this gymnastic. And now you correct the intensity without changing the color, because the RGB stays. If you take the RGB and multiply by constant, it will look more or less the same thing. Again, take a pixel with some color, with some RGB, multiply the whole RGB by 2, it will look more or less the same color, just more bright. And now we are getting the output, which is the corrected one. And it was cool because there was no AI, not that it cannot be improved, but there was no smart decisions about which regions needs to be fixed. There was no segmentation of the image. It was all in real time and with very, very slow, very old analogous technology, if you wish, and very little brain power, no decisions out here. It was the HDR that happens online without any decision. Well, you need to massage what are the parameters alpha, beta, gamma, what do you call as high frequency and low frequency, but what is the size of the Gaussian that you want? More Gaussian means more blurry, less blurry. That is what do you think about high changes or low changes? So it's all parameters that you can play with, but it's 5 numbers that you fix them and it works for the whole image. There is no intelligence that works on analyzing what happens in every part of the region. There is no classification that says, oh, that's very bright, so I don't need to change it that much, versus that's very dim that I need to add something. No if. Nowhere in the code was the command if appeared out there. So it's a beautiful algorithm.
Would you like adjust the intensity for like a pure red pixel, right? Because it could be like dimmer than a different pixel that has like some of every color, but like if you try to increase the intensity, then you just overflow the red value, right?
So it's always, if it's more than 255, hopefully I did the alpha beta in the whole thing. When I did the alpha beta correction, I put it so that it's in what the monitor can present between the lowest and the highest of the monitor. And actually I think I'll put it even with a bit more safety margin. So even when I'm putting age back, adding age back, it's still within what the monitor can present. But at the end of the day, I need to truncate the values, and I need to clamp them so it's not less than 0, which it can definitely be, and it's not more than 255. So there is clamping at the end of the day that says if it's more than 255, then you just say 255, JavaScript just says the command clamp, I think. Cool, and you have the nice slide that summarize all of it. And maybe it will be homework 6, maybe it will be part of the homework 6. I'll tell you Wednesday. How are you doing with homework 5? Need help to chat about? No. Okay, so yeah, go home. I don't think that we have much more in the dynamic range. Yeah, that's all that happens in the dynamic range. You know the whole algorithm. Another beautiful example, original image that we cannot see. Yeah. Original image that we cannot see. Way too overexposed or way too underexposed. One in the algorithm that I showed you, that's a result. So you had the low frequencies that, well, it classified, but without knowing about it. This area is too illuminated, this area is too dark, so that's where we are doing the compression, but all the details of the things hanging from the ceiling, all of them were stayed, I guess, in the high frequency, so they were not compressed, and that's why when you're adding it, all the details pop up. Okay, yeah, go.
Bye, thank you.
Bye-bye.
Yeah, just a quick question.
Oh yeah, there is a coming up after that about the hello nightmares, but that we talk. That's a cool idea in general. Yeah.
Yeah, so I got the water working pretty good, I think. The only thing is, I don't know, maybe should do. I was wondering, is it important that the waves are somewhere? Yeah, there. It's important that the waves are centered at the on the pool, because I kind of got it.
I will take 1.2. Oh, that's cool. That's so cool.
Yeah, yeah.
It's very pretty.
Yeah, I got
send me a
the
video of
demo.
it, anyhow, and the link, because that's, you need to see what he was doing, combining. That's very cool.
Yeah, it's,
Like you through the whole, I'm very careful not to phrase it as a question. If it's you implemented the whole thing, that's
yeah,
fantastic.
no, I've been trying to do it
I'm careful
continuously.
not to ask. That's really pretty. Yeah.
Yeah.
So, but what's the geometry? The waves.
The waves are
that
kind of coming from like somewhere out here.
I don't care.
Okay, cool.
That's absolute.
Yeah, same with this.
You look. I suggest to put it in the middle of the pool because it's easier to debug. Then you expect things to appear there radial.
Okay, cool. Yeah, I did the skybox.
But if it works, it works.
Just
Yeah,
like 6
that's cool.
billboards.
That's OpenGL or
OpenGL, yeah.
or WebGL.
WebGL, yes.
Because okay, so that yeah, then I should. Yeah, then I'll play with it because OpenGL I thought was a bit stronger in the box thing, but
Yeah, to do a WebGL, you would have to to actually get it right. You'd have to do like a ray marching to see if it's because it's hard to find get into the fragment shader if you don't have a collision.
yeah, that
So you
that
use
it shows you.
OpenGL for that?
No, I use WebGL, but actually
Okay.
I put 6 billboards all around, and that's how I
So
did
you
the
did.
skybox.
So yeah. So you see that there is a gap
Yeah.
between one wall to another. Not that's fine. In
Yeah.
WebGL theoretically, it. Yeah. I don't have anything to say.
Okay, cool.
Maybe the parameter and things that it's all
Yeah,
cool, but
should be- Yeah.
Phyllis, that's why.
What is it?
Yeah. So why shader programming is that
Nice.
every vertex, every fragment shader, every pixel shader, decide for itself all in parallel for every ray where it's coming from the sky, and then assign the correct color
Really?
based on it, and it all happens in parallel. Yeah.
Yeah, you can even do the.
Cool.
Oh, wow.
It's kind of sheety double reflection because one of them is the screen space and one of them is the box. So.
That's so sick.
Yeah.
Amazing.
I mean,
Oh, that's with reflection. So yeah, that's a cool. So you can also see the water wave. There is a painting at the bottom of the pool, and you
Vibrant
see
colors.
how the different wave of the water. Okay.
Yeah.
Yeah.
Funnily enough, when you turn the amplitude
I
up.
think my son can look at that, stare at that all day long. Bright colors.
And yeah, maybe. So did
Is it
it
in
make any sense?
OpenGL?
Yeah, WebGL.
WebGL? Yeah, that's right.
Yeah.
Yeah, I mean, for our purposes, OpenGL I think is easier. It's easier to debug. WebGL has lots of hacking.
Yeah,
Yeah.
it's all-
So
you have to write JavaScript, though, right?
Yeah, I did JavaScript. I do TypeScript actually, but.
Okay. Oh, TypeScript. Okay.
Yeah.
Does it make any sense to have something like what I said at the bottom of the pool? This one and the something much simpler than this one, and maybe I'll let you choose. So that's the top of the pool without the
Who's the better
part, and
basketball
then
player?
you
I
have
took
a
it
lava, a bulb coming,
Oh,
and
yeah, yeah.
so there are a few bulbs that are coming, so the surface have to do. So every pixel knows what its elevation can change a bit based on the surface, and the surface can change. There's some animation to do this stuff. So maybe it will be instead of the HDR. With the HDR. Yeah.
I have no question. I'm just
This costs us so much
checking
money.
something.
It is. It is.
I-
You want to show?
Nope. I'm just, I'm working on a.
I think it's web video
Yeah,
games.
web app right now, web stuff.
Back in the old days. I had to write all this rendering myself. Back in the old days.
I'm sorry.
Jason found the video games that I wrote, and he was totally fascinated. He was like asking me about it. How did you do this?
What will how?
Super Nintendo. Long
Okay,
time
but
ago.
what did you run it on?
It was just a CPU. It was a 6502, like an old Apple IIe
Yeah,
processor.
but today,
really.
what are you running?